Assalamu alaikum. Student, today's lecture about operator, linear operator. We give definition of operator, linear operator, null space of T, kernel of T, and give some examples with verifications of linear operator. And we prove one theorem related to linear operator. Uh, Now we start a lecture from the definition of operator. An operator is a mapping from a vector space to another vector space over the same field. Uh, what it means? If we take a mapping from one vector space to another vector space with the restriction both vector spaces having same field, then this type of mapping is called operator. Now we define a linear operator. Linear operator is an operator. What type of operator is called a linear operator? A operator is said to be linear operator. Number one, if domain of T is a vector space and range of T lies in a vector space over the same field. And second condition is for all xy belongs to domain of T, scalar and scalar alpha T into x plus y is equal to tx plus ty for all xy belongs to domain of T. Also, T into alpha x is equal to alpha times T of x. What these conditions means, if we check some operator is linear or not, we check these two conditions. If this is equal to this and this is equal to this, this condition is if we add two vectors from domain of T, then apply T, then this image is equal to if we apply T on x and then apply t on y and then add, then this answer is equal to this. Similarly, here if we apply multiply alpha with x scalar with a vector x, then we take image under t, then this answer is equal to if we first apply t on x then multiply with alpha. Here d of t denotes the domain of t, r of t denotes the range of T, and n of T denotes the null space of T. Now we define null space of T, where T is a linear operator. The null space of T is the set of all those elements of domain of T such that T of x is equal to 0. This is the collection of all those elements of domain of T on which T giving answer is 0. Another word for null space of T is the kernel of T. We can use kernel of T or null space of T. What is this? This is the subset of domain of T on which T gives answer 0. We denote it n into T. And this is symbolically defined. N of T is equal to the set of those elements of domain of T such that T of x is equal to 0. And these are remarks. These two conditions of linearity is equivalent to this single condition. Yani t of x plus y is equal to x plus tx plus ty, and t into alpha x is equal to alpha t of x. For all x y belongs to domain of t, and for all alpha belongs to f, and for all x belongs to domain t. Uh, these are valid if and only if t into alpha x plus beta y is equal to alpha t of x plus beta t of y. If this is true, then this is true, and this is true. This really, we drive this condition from these two conditions, and we drive these two conditions from this single condition. And this is the verification. Let t into x plus y is equal to tx plus ty. This is the first supposition, and second supposition is t of alpha x is equal to alpha into t of x. These two suppositions we suppose is the first part, and we drive this equality. We know alpha beta belongs to f because x and y are elements of domain of T, and domain of T is a vector space, so alpha x and beta y are elements of domain of T. Since domain of T is a vector space, so alpha x plus beta y is also a vector of domain of T, is an element of domain of T. Now, If we apply t on this element of domain of t, then then this is equal to t applying on alpha x plus beta y, which is the element of domain of t. This is equal to t alpha x plus t beta y by first supposition, and by second supposition, we get an take alpha decide alpha t of x plus beta t of y by second supposition, that implies t of alpha x plus beta y is equal to alpha t of x plus beta t of y. Now we suppose if for any xy belongs to domain of t and alpha y alpha beta belongs to field f, t of alpha x plus beta y is equal to alpha t x plus beta t y. Then we want to prove uh, two conditions. By taking alpha beta is equal to 1, this condition, this equality changes into this tx plus y is equal to tx plus ty, and by taking beta is equal to 0 in 3, t alpha x is equal to alpha tx. So the upper two conditions is equivalent to the single condition. We derive one from another. As we know, t of alpha x is equal to alpha t of x. If alpha is 0, then t of 0 is equal to 0. Alpha, if we put alpha here 0, 0 multiplied by x, answer is a 0 vector. Here alpha multiplied by t of x, and alpha is 0, then 0 multiplied by t of x, answer is a 0 vector. So if we take t as a linear operator, then the answer of a 0 vector always 0 vector under linear operator. This is one of observations. And now we take examples of linear operator. First of all, first example is the identity operator. The identity operator I is from x to x is defined by I of x is equal to x for all small x belongs to greater x. By identity, proof identity operator is a linear operator. Here we give the proof that identity operator is a linear operator. This is a very simple example. I of x plus y, we take two elements, x, y belongs to s, and apply I on x plus y. By the definition of linear operator, I of x y is equal to x plus y. We can write x is equal to ix and y is equal to iy because I is an identity operator. So that implies I of x y is equal to ix plus iy. Now, for the second condition, for alpha belongs to f and x belongs to x, I into alpha x is equal to alpha x by definition of identity operator, and we can write x is equal to I of x by definition of identity operator. So I of alpha x is equal to alpha I of x by 1 and 2. We can say that I identity operator is a linear operator. Now take another example. Uh, Zero operator. Another operator O from x to y defining by O of x is equal to zero, a vector of second vector space for all x belongs to x is called a zero operator. How operate zero operator? When we operate O on x, which is called a zero operator, the answer is a zero vector for every element of x. So these are very easy to check. Mm, this is a linear operator, two conditions are satisfied. So there is another example, differentiation operator. Let's be a vector space of all polynomials on AB closed interval. We define linear operator T on X by mm, T apply on XT. What is XT? XT is an element of vector space. X means this is a polynomial. When apply T, it means we take its derivative X dash T for all X belongs to T. So when we apply t on any polynomial, mean element of x, then how t operates, we take its derivative. So this is again a polynomial. Um, this operator maps x into itself. Prove that t is linear. So linearity can be checked by these two conditions. So by the information of basic information from first year, second year mathematics, when we take derivative of addition of two functions like f plus g is derivative, this is equal to uh, first derivative plus second derivative. Any d or d over dx is equal to g plus y, g plus h is equal to d d of h dx plus d over dx g. G plus h derivative is equal to derivative of g plus derivative of h. So by this information, and if we scalar is multiplied with some function, say alpha f is a function, then derivative of alpha x is equal to alpha times derivative of x, and derivative of alpha x is equal to alpha times derivative of x. By this information, we can write uh, this into this form, and by this two conditions of linear operator is satisfied. Now this is the integration operator. Uh, Let x is equal to CAB, then the operator t from C to R, defined by t of x is equal to integral xt dt. Integral moves from a to b. Lower limit is a and upper limit is b. T belongs to closed interval ab, and x belongs to uh, space CAB. Then this by using the basic information of integration, addition of functions integration, and if some function is multiplied with a scalar, then its integration as information, we can easily prove that integration operator is a linear operator. Here, these are some steps, and we prove that. Next example, that x is equal to CAB, then the operator C from C2 defined by T of xt is equal to TXT, where T is fixed. Here, T is fixed element of AB closed interval. If we choose, then it is fixed. Then when we apply T on element of C, mean some function xt, then this T multiplied by this function. So this definition is also satisfies the two conditions of linear operator. From elementary algebra, the cross product with one factor kept fixed defined a linear. This is also an interesting example of linear operator. T is a mapping from a vector space R3 through R3. How it operates? T operates when T operates on X, I mean a vector of R3. Then we take a cross product of X with R. What is A? A is a fixed vector of R3. If we once we choose, then it is fixed. So when we apply T on element of X, then how it operates, we take its cross product with the vector a. A is a triplet, and x is also a triplet, but a is fixed. Then this cross product is a which is a definition of t is a linear operator. We can easily prove this. Check, this is the application. When we apply this again, this is the knowledge of our cross products knowledge. When two vectors are added and take its cross product with one vector, this is equal to the first cross product with a and second cross product with a, and then their addition. And but simple steps, this is a linear. In another example of a dot product, T from R to R3, A vector is a fixed element of R3. Take any x of R3 and applying T on x, then x dot, this is equal to x dot A, means the components wise multiplication and addition. A is equal to A1, A2, A3, and x is having components x1, x2, x3. Dot product is x1, A1 plus x2, A2 plus x2, A3. So this is the element of R, and this definition also satisfies the properties of linearity. Similarly, if we fix a matrix with R rows and n columns, uh, And then this defines an operator, the definition of operator, T from Rn to Rr. T of x, x is an element of Rn. They apply T on x, this is equal to A multiplied by x. A is a fixed vector, once chosen, then fixed, and x is an element of Rn. The answer is y is a R tuple, element of Rr. Then this by these steps we can also say this is a linear operator. Actually, here we use the knowledge of basic mathematics like maths in first year, second year FSC. We can read if the two vectors are added and by some matrix is multiplied by these two, then this is equal to this. This matrix multiplied by this matrix and this multiplied by this matrix. By using this knowledge and this information, we can easily prove that this is linear. Now, here is very important theorem related to linear operators. Focused on statement of theorem. Yes, theorem states as let T be a linear operator, then the range of T is a vector space, number one. Number two, if domain of T is equal to n, mean if domain of is finite less than infinity, then the range of T, dimension of range of T is less or equal to n. Number three, the null space of T is a vector space. So one by one we prove. Now first we prove A we take any two elements y1 y2 belongs to R of t. How we prove? Because in the definition of linear operator we say domain of t is a vector space and range of t lies in a vector space. Because range of t lies in a vector space, for proving range of t is a vector space, we just prove this is the subspace of a vector space. So we take by using the condition of a subspace, taking two elements from this set and taking two scalars, and then make their linear combination and show this linear combination belongs to the set which we are going to prove a subspace. And this is true for every two elements of that set and for every two scalars. So here we take v1, v2 belongs to R of 2 and show that alpha y1 plus alpha beta y2 belongs to range of t. For any scalars, alpha beta belongs to f. Since y1, y2 belongs to range of t, we know y1 is equal to, we have y1 is equal to t of x1 because y1 is an element of range of t. So y1 must be image of some element of domain of t. So say this element of domain of t is x1 and t of x1 is equal to y1. Similarly, y2 is also an image of some element of domain of t. Say this element is x2, so y2 is equal to tx2. For some x1, x2 belongs to domain of t. Because x1, x2 belongs to domain of t and alpha, beta are scalars and domain of t is a vector space. So alpha x1 plus beta x2 is an element of domain of t. Because domain of T is a vector space, by the linearity of T, we're applying T on this element of domain of T. Then by linearity, this is equal to alpha Tx1 plus beta Tx2, and Tx1 by our supposition is equal to y1 and Tx2 is equal to y2. So we prove T alpha x1 plus beta x2 is equal to alpha y1 plus beta y2 because this element is an image of this domain's element. So every image of domain's element is an element of range of t. So this element is an element of range of t, and we can show that this linear combination belongs to range of t for any two elements of range of t and for any two scalars. So by the condition of subspace, a range of t is a subspace and so is a vector space. By second, now we prove B part of this theorem. For this, in B part, we want to prove if dimension of domain of T is n, then we want to show dimension of range of T is less or equal to n. Contrarily, we take n plus 1 vectors of range of t, and at the end we show this set of vectors does not perform basis of a range of t. Why? Because these does not remain linearly independent, and uh, for basis it is necessary that the set performs the basis must be linearly independent. So we choose n plus 1 elements of range of t in an arbitrary fashion because these are elements of range of t. Same reasoning, there are n plus 1 elements of domain of t, and these elements are the images of these n plus 1 elements. Say these elements are x1, x2, xn plus 1. T of such that t of x1 is equal to y1, t of x2 is equal to y2, and t of xn plus 1 is equal to yn plus 1. For some scalars, for some x1, x2, xn plus 1 belongs to domain of t by the definition of range of t. Since dimension of domain of t is equal to n, the set x1, x2, n plus 1 vectors of domain of t must be linearly dependent. Why? Because dimension of domain of t is n. So any set of vectors of domain of T whose length is more than n elements is must be linearly dependent. Hence, if we take linear combination of these n vectors with 0, then one scalar must be non-zero because of linearly dependency of the set of vectors. So some alpha I not equal to 0. Since t is a linear operator and we know t of 0 is equal to 0, if we apply linear operator on a 0 vector, the answer is 0. Apply t on both sides, here and here. Apply t here, and t here, then t of c is 0, answer is 0. If we apply t on left hand side and t is a linear operator, then this is equal to mm, alpha 1 tx1 alpha 2 tx2 plus alpha n plus 1 txn plus 1, and tx1 tx2 and txn plus 1 is equal to y1 y2 yn plus 1. So this change into this alpha 1 y1 plus alpha 2 y2 and plus alpha n plus 1 yn plus 1. And because we apply t on both sides of this equation, so t of 0 is equal to 0, mean this linear combination is equal to 0 with at least one scalar not equal to 0, and this shows y1, y2, yn plus 1 set of vectors is linearly independent. So this does not perform the basis of range of t. Hence, if we take any set of vectors whose number of elements more than n, which is the dimension of domain of T, then this set of vectors, in the same way, we can prove this set of vectors is linearly dependent, so it does not perform basis. So the dimension of range of T must be less or equal to n, which is the dimension of domain of T if T is linear. For the third part here, this is the third part. We can prove that null space of T is a vector space. Actually, null space elements are coming from domain of T by the definition of null space of T. So we just show null space of T is a subspace of domain of T. So we take two elements x1, x2 from null space of T, and by the definition of null space of T, x1, x2 are actually elements of domain of T, and T of x1 and T of x2 answer is 0 by the definition of null space of T. Since T is linear for any scalars alpha, beta, we have T into alpha x1 plus beta x2, and apply the linearity of T. Alpha tx, this is equal to alpha tx1 plus alpha beta tx2, because tx1 tx2 is equal to 0. So this term is 0, 0 multiplied by alpha is 0, this term is 0, 0 multiplied by beta is 0. So in totality, T of alpha x1 plus beta x2 answer is 0, because due to domain of T is a vector space, so this is an element of a vector space. It is a domain of T uh, whose image giving answer 0, so this element must belongs to null space of T by the definition of null space of T. And by this condition, because x1 x2 are arbitrary elements of null space of T and alpha beta are any scalars, So, by proving this condition, we can say null space of T is a subspace of domain of T, so is a vector space. So, student, this is today's lecture. Take care. Allah Hafiz.